Yeah, so we have to speak into the mic, otherwise they won't hear the record. So if you put that, 那个, the waist, the thing, yeah, clip, and then share your screen. Yeah. Open systems. Yes. Would like to record this screen. You have to allow it to, because otherwise 它不能. Yeah. Yeah, you can put it wherever you want. Then, but the clip, put it, yeah. 然后就其实这样就可以了. You will feel like 好像没有抓到, but then 其实它有. 对，因为 it doesn't want to be too loud, 不然就会有一点太过度这样子. 所以其实它是 OK. Okay, so I see you on the Google Meet, so then you can, whenever you're, you can share. 哈？好多视窗。对啊， so so 有时候 technology 太强，我们也不知道到底要怎么样用，所以 it's very confusing. But it's okay. Let me see. Okay, so 大概是这样子啊. I mean, we're gonna record this session anyway, and so people who are online or in the lab, 其实这个是比较是为了 for 我们自己 lab, mostly for our own lab. So, but we figured that since we are doing it, we can also share it with whoever is interested in the bigger BrainHack school community or imaging community or whoever. And because this is a tool that we already have published, so I think we can share it, no issues, and hopefully other people can use it for their own projects as well. And also, we are also continually using this thing also, right? Yeah. So I think, I think it's fun. And then of course, if people here who are live here wants to ask questions, it's not a talk and it's not a like, 我们不是要 present or anything, but 就是说 actually more like 一个 discussion session where you go through this thing, 我们顺便 record. 在以后就是那个 lab 要用的时候, if there anything 我们可以看 refer back to this video for the technical thing 这样子. So 只是其实比较多是为了记录 and 一些简单的 demo as opposed to 一个 talk. This is not a talk or anything. 对. So OK, 那 in that case 我就交给你那个君威 is presenting for or sharing her script that she used to do the multi-voxel state transitions, and then she has the GitHub on there, and we can follow along. Okay? Right.
Yeah. So, does everyone has this link to the GitHub? So when you click, and then this page will show up. And then we can scroll down to see the README first. So this one, I name it state MDS because we are going to use multi-dimensional scaling analysis to visualize the dynamic trajectory of brain network states. And we use resting states fMRI data, but actually you can use any functional data to apply this method. And so here's the main concept. So what is functional states? It's defined as a spatial pattern of multi-voxel activity, which is both signal, and captured at a single time point, which is TR. So in our resting states, functional MRI is every 2 seconds we have the whole brain scan. So every 2 seconds, we define as functional states. Then we record this temporal change in this multi-voxel pattern. And we want to capture the dynamic trajectory of how this network activity. And then we use these multi-dimensional scaling methods to transform from high-dimensional Voxel-wise pattern to like 2D, 3D, or 4D, this lower dimensional space. And these methods you can apply to any network of interest or any atlas. So in my first paper, I used the AL3 template to define default mode network and salience network and action network, whatever. And now I'm using the FUMO atlas as a mask to capture the dynamic change within each mask. So, and any questions so far? Huh? Yeah, but not here.
In theory, also you can do it on the whole brain.
Yeah.
I mean, anything that you can make it into a vector of states of a particular time point, right?
Yeah.
Yeah. And I think some people might be interested in applying it to maybe even EEG electrode channels, or MEG, or FNIRS, or anything like that. Yeah.
Yep. And here it comes to this structure of this GitHub. So I have data outputs, MATLAB, R, and the R projects, and README, which is this file. And for the data, I also have 2 subfolders, which is row and voxels. And row is for I provide one sample of 4D EPI volume and another sample of the mask. So you can extract the values from each voxels under this mask. And then the voxels is for these states NDS, the input data. So here, I think I gave 8 participants as example in the GitHub. And then output file, we can talk it later. And the MATLAB is because when I try to extract the values of each voxels, I use MATLAB, and I use these carry voxels, which is
lab stuff. That's our lab stuff, right?
Yeah. It's written by Yuxiang.
Yeah, you can get it. I think there's also the GitHub. He has a GitHub. Or how did you get it? You got it from him?
Yeah.
Or did I give it to you?
You had this GitHub.
Yeah, there's a GitHub somewhere also.
Yeah.
Yeah. I guess we can find, is it searchable? Can you Google it and then maybe it will appear as a link?
Really?
I don't know. GitHub. Carry in. carry.
Carry.
Or it may not appear. There, the search,
Well,
you know.
My
Don't have
other screen.
Okay.
I can attach it later.
Okay, all right. Anyway, it's a in-house script, MATLAB script.
Yeah. So this script is how I get my input file, which is CSV file, prepared for me to apply this state MDS method. So, and then the R is the main analysis here. So the first file is run MDS analysis, which is the main MDS pipeline. And then the second one is calculate brain indices. And this one is after you get the results from the first one, we are going to introduce more advanced analysis to show you as example how you apply these numbers into more advanced indices. And the third one is visualize trajectory. So this scripts, this code I provided here is for you to kind of like visualize how data looks like for each subject. And because for us it's easier to view as a 2D, 2-dimension and 3-dimension, so here I only provide these 2 dimensions. And the fourth one is plot state space heat map. And this one is actually related to the second one, the brain indices. So the fourth state space heat map here is for the grip entropy, which I will mention later. So don't worry if you have no idea about this. So this one I just want to show you how, like if one subject with higher entropy and the other one is lower entropy and how it looks like in the 2D map. And the final one is the plot LAM plots. So this one is also relevant to the second one, the advanced brain indices. So this one is LAM, the full name is laminarity. So which means how these subjects, how their brain states, if they always like stuck to the certain states when the time moves, then this index will be higher. Like if the brain state doesn't change much, you always like maintain the similar states, and this index will be higher. So the final scripts, I just want to show you how if you can plot a map and how it looks like. Okay, and requirement, blah blah. You can have a look. And so this is the main packages for my R scripts. And I think you can, I don't know, if you want to like practice right now, you can download the whole packages into your laptop, and then we can run. Okay. I don't think so.
It's just one volume, brain volume.
Yeah.
So yeah, should be all right. If people want to have question, you can just get a mic and then just ask.
Okay. Okay, if you download the whole packages, and the first step is to click this R projects. So it would like direct you to the correct directory. So here, okay, so this is the main MDS analysis scripts. So here is just for the define the input-output folder, and then create the directory if they don't exist. And the second one, configuration, which is more important here. So for dimension, you can choose any dimension you want to do. So here I just type 2, so it's 2 dimension, the output. And you can type 3, 4, 5, 6, whatever you need. And max TR, because in my data sets, they come from many different projects. So the resting states parameters, they're usually not the same. So I just need to get the minimum number because it would be fair for everyone.
The dimension is, you set it here.
Yeah.
Isn't there where you have to search how many dimensions that is suitable? That's something else?
Yeah, you can, yeah.
So it's not here, or where is it?
Well, I didn't think it much. I just like, you can type here. But yeah, you are right. You can go through your data set and find the minimum number of TR.
Oh, okay. No, dimension, not TR.
Dimension.
Yeah. Because there's like some people might be using 3 dimension or 4 dimension, right?
Yeah.
How do we do the, what do you call that? The stress plot, the stress. Is it here?
No.
Oh, something else. Oh no. How?
I just provide the straightforward.
Okay. Oh yeah. Let's just. Okay, we work with 2 dimensions. Assume first everyone is 2 dimension.
Yeah. First.
But then later we can talk about if we have more dimension.
Yeah.
Okay. All right.
Okay. And then the rest of it, I don't think you need to change. Okay. So if I run this, and you will tell you like which subjects right now. And then if the analysis completes, you can save in this folder. And I just, okay. So for the input file, is this one? Yeah. I just want to show you an example. So the columns is the value for each voxels, and each rows means how many TR you have. So in this matrix, it should be like 180 rows, and then the voxels depends on the mask you want to look at. And it also vary between participants. So if the participant have different columns, don't have to worry because it's common. Okay. So then we can see the output file. So in the output file, I provide these 2. So this one, arrow distance, yeah, I can open it to show you. So this one, I think I should open this one first. No. This one is already like after MDS.
Oh, after MDS, you get the CSV file.
Yeah.
Okay.
So this one, MDS1 and MDS2, is the dimensions, because we set the dimension as 2. So
okay.
we have like 2 columns here.
Okay.
So,
So you have 3, then there'll be 3 columns.
Yeah.
Okay.
And 4 columns,
Okay.
whatever. And then, so it will be like 180 rows, but because the first row is the name, so it goes to 181. So each one, the number here, it means the coordination of the map.
Mm-hmm.
So you can imagine MDS1 is x-axis, and MDS2 is y-axis. So if you plot them on the map, it will be like many dots, and it will be 180 dots. Okay. And then the other file, the arrow distance, it means I calculate the distance between each dot continuously. So the first dot to the second dot will be like 5.268, something like that. So I got all the distance between all the dots. Okay. So, yep, so there will be 179. Okay. And then I also provide you another like summary file. So this one, the first column will be like how many subjects you have and their ID number. And then the second one is the velocity total, which means like how far, how much distance they change throughout from first point to the final point. And then the mean means like the total distance here divided by the TR. Yeah. So actually this column and this column should be the same, just the ratio. And then the stress, it means, because when you run the MDS, they have the stress level to tell you like if this dimension makes sense for these subjects. Yeah.
So from here, you have to do it like a few. And then from here, you choose for this subject how many dimensions. Yeah. Okay. All right.
So here, you can see the first participant is 0.08, which is quite low. Like in my first paper published last year, we choose the threshold as 0.15. So if the stress level below 0.15, I use that dimension. Otherwise, I will go up to look for the suitable dimension for these subjects. So I think for younger participants, usually like 3-dimension or 4-dimension will be enough. But for the older subjects, I found the maximum will be 6 dimensions. Okay. So you can try and then find the suitable dimension for that subject. Okay. So the next one is okay. So it's pretty much about the first R code here. Okay. Any questions? Yeah. So then I will open the next R code here, which is the calculate the brain indices. So, wait, I want to change the order. So the second one I want to introduce is visualize trajectory. So here I will apply the MDS coordination to plot on the 2D plane. Okay. So here, so here the setup path. So subject ID you can change here, but later on you can modify this code to like apply all the subjects to plot everything. But here I just show you one example. Huh? And yeah, you can do it, but I think you can go for the loop. Yeah. You can just use Gemini to modify the code. Yeah, now I want to apply all the subjects to plot everything, how to do it, right? So here, I just use the first subject's results to plot this. So before this R code, you need to run the run NDS analysis to get the NDS points in order to visualize the trajectory. Okay. So here, I also run, blah. So I provide 2D and 3D here. So here you can click the plots here. So you can see there's a 2D plan for the first subjects, how the trajectory look like. Yep. Okay. And then I also plot the 3D. So here, so 3D, it means it's still like result is 2D, like NDS1, NDS2. I just add the time as the z-axis, so you can see this.
Is this a young subject?
Huh?
Who is this a young subject?
Yeah. No. Oh.
No. Oh. Looks very beautiful.
Yeah.
Yeah. Okay.
Yeah. Okay. Actually, in the assets, I think yeah.
That one is the one where it's not beautiful.
No, it's.
So
I'm not sure whether this point is just relevant to
Sure.
the motion.
maybe
or
head
something.
motion. Sure.
Yeah.
Yeah.
But because yesterday I tried to find a perfect example
Yeah.
for the high mean velocity, like
Yeah.
they move a lot
Yeah.
during this time period,
Yeah.
and compared to they don't move much. And this one, the
Move a lot.
data is, it doesn't move much. It's just like several time point, they just put and then come back.
Mhm.
So most of the time they kind of like wandering here.
Sure.
And then
So, which is a good point to warn people that actually we have to be very careful with head motion, because obviously that motion there doesn't mean anything psychological or computational. It's just because the data signal move. So before all of this, actually, there's a lot of care taken to make sure the data are cleaned up. And then even after this, we also include motion covariate still. Motion is always a terrible thing for such data, especially racing state, since we don't have a design or experiment to tell what they are doing. So, yeah.
Yep. So, okay, so this is for 2D and 3D trajectory. So this is pretty much about this script here. Okay, so the next one is calculate brain indices. So here I provide like 3 different brain indices here. So the first one is, I think I'm gonna use weightings. So the first idea, we want to see like from this map, this 2D map, I want to see like the area this participant's mind has traveling through this period of time. So we kind of like try to calculate the surface. Surface? Manifold. So we try to calculate this area, like 面积, right? So yeah, the whole size of the shape. And so here, so the first one I use this is a convex whole area, and the abbreviation is CHA. So how much area they cover through this time period. Okay, so we try to calculate the area, which is the first index here. And here is the example, like this one just has smaller CHA, like they travel less, and this one's travel a lot. Okay. Okay. And then the second one, which is the entropy, like we calculate grid entropy, like how complex is this person, these functional transitions. So you can imagine like here in one 2D plan. So I think the way they calculate is like they divide this area into many different pieces, and then they calculate how many times they travel to this piece. So if the color is more warm, which is like super red 8 times here, it means like this person, like my functional states, travel to this point for like 8 times. Right.
How do they decide how big the square are?
I'm not sure.
So when in the code, is there something that does it, like
I
some setting or
I
whatever?
think so.
Okay.
Each voxel, each
Yeah.
size, is that the one you showed before and the other trajectory? What was that? Another figure just now? Is this the same one?
Oh, you mean this one?
Yeah,
No, different.
different one.
Yeah.
It's like, I think, so just now the one, the grid entropy, this one, you put this line, rotating thing onto that grid. And then because each grid is a position, right? X and Y, right? So how many times the dot in the line fall into that square?
Oh, I
So
see.
so that's why I ask about the size.
So each
right.
dot doesn't represent the one voxel. It's
No.
one voxel is actually how many times that the
Mhm.
dot
They travel
visit.
is
that
inside
point.
that
Okay,
voxel.
okay.
Yeah.
Okay.
Or pixel, in this case it's 2D.
Okay.
But so that's why I asked about the size. Because if the pixels are very small, then most should be 0, right? Except for a few. But if the pixels are bigger, so it's coarser, so then there'll be more opportunity for a dot to fall into the pixel. So the resolution of the grid obviously will come into play. But I assume the script has some way to adjust or account for
Yeah,
this.
I asked the script to normalize.
Yeah, yes, exactly. You have to do some normalization to account for the size and all that, so that it makes sense across different patterns.
Yeah.
Otherwise, it's not fair or whatever.
Yeah. So here the grid entropy is my second advanced brain indices here. And then the third one is the laminarity. So this one means like, so here, it means how your brain stuck in one place for a long time, right?
So this also will depend on the previous one, right?
Yeah.
So it's like you first have a grid of voxels or pixels, and then if the points are in that location now, and then the next instance is still in roughly the same location, then it'll be a +1 or something.
Yeah.
But if it's moved to another, then it is back reset.
So
from
it
there.
also depends on how big is your
And how
grid
big-
is.
Yeah, okay. All right. And this one is all grid, so like the area is always a square grid. Because if you remember when we were talking about the other group, they do the reversibility paper, the one where they do the low detailed balance, that paper. And
The broken.
broken detailed balance, that paper. I think it's similar, except that they don't use a grid, they use a Gaussian kernel. So it's not always, it's either xy 1, 2 or xy 1, 3 or x, but it's a smooth function. And then, so there is a probability rather than a
Yeah.
count.
Yeah.
Yeah. So, but the principle is the same, I think.
Mhm.
Yeah. It's very cool. Okay.
So here is just a plot example. Like the left side is like the person with higher LM. It means like because diagonal means it must be like 1 because it's the time point to time point. So the 20 time point to the 20 time point, it should be 1, should be the same brain state. So you can see like close to this diagonal line, if they are darker, it means this person's brain stays stuck more. Yeah. And compared to this one, the lower, it has low LAM value. The diagonal line is like not much black dots. Okay. So we back to these R scripts to calculate the brain indices. So I introduced these 3 different indexes. So we can run this R code to get. So
We can just run this. When we download the thing, we can just run it. Or
yeah,
do we have to set the path or whatever?
No, you
Oh.
can just.
But I just got some error. Never mind.
Oh.
It doesn't. It says it doesn't have here, the function here in my version. Or maybe it's because I didn't install it. Okay. All right.
I think so. Okay. So the output will be like output folder, and the file name is brain indices summary. So let's open this one. So it'll be here. What's going on outside? Do we need to evacuate? So this summary file, again, the first column is subject ID, and the second column is CHA row, the space index, like the area, like how much surface they travel during this time period. And row means before normalize, and then this one is after normalize. And GE is grid entropy, which calculate the complexity. So rho, it means before normalize, and norm means after normalize. And LM, I don't know, they always normalize, so they don't have rho. Okay. So we got this 5 columns as a result. And you can use these results to try to see how their behavior indices correlates with. So from my previous study, I haven't correlated this one, but before I correlate the mean velocity to the psychological resilience, and we found if your psychological resilience is higher, your mean velocity will be lower. So it means like you travel slower during these time periods if you're more psychological resilience. And currently I'm working on the behavioral index is cognitive variables. And we also found if you have lower mean velocity, your cognitive performance will be better. So it seems like you don't change much, it's better for you. Okay. And for these advanced indices, I think this CHA is kind of similar to mean velocity, right? Like how much you travel around. Okay. And then for the grid entropy, I don't really remember. So
like for the whatever area you have, the how many states you are in. So that was also like you don't want to be in too many states, right? You want
Yeah.
to be in the fewer states or something like that.
Uh-huh.
Oh.
And anyway, in my current data sets, I compare older
Yeah.
adult and younger adults. And older adults tend to have smaller, I don't remember. Yeah, smaller area they travel compared to younger adults. So younger adult kind of like travel more during this time period, and older adult kind of like travel not much. But for the re-entropy, the older adult is higher. Like they kind of like jumping around within this small area. And then for the liminarity, also the older adult is higher. So, which means their brain state kind of stuck at stuck somewhere through the time compared to younger adult. And then I think we move on the next one, this. So plot state space heat map is to plot the gray entropy into the 2D plane. So the thing is, these scripts, you can plot for whole subjects, and you can find in the folder, in the output, and then plots and GE heat maps, and you can find all the subjects, the heat map. And I also, for the caption here, one subject is like 2 types, okay. So subject 1 and the heat entropy row, not heat, grid entropy row, and then I also show the after normalized number. So you can see like they kind of different.
So that third one, the S6, subject 6 is the one with the sudden
yeah,
head
yeah.
movement, right? This one.
Yeah.
Yeah. Okay. Cool. I guess it's kind of like the shadow or the silhouette of the trajectory. Like if you project a shadow, right?
Yeah. Okay.
Cool.
And then the final scripts is to plot the liminarity. So this one, I also provide a script for you to plot all subjects. So you can basically just select all and run, blah, 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 and then you can go to output file folder, plot folder, and LM plot. So here you can get all the subjects LM plot. So this subject has higher compared to this one, and then it's kind of in the middle and less. In the middle, and here is more. Something like that. Oh, it's less. Okay. I try to find a participant with like higher contracts, so you can have a look how it looks different.
Yeah, I think that's the point. It's like these things are, I think the key contribution here is that in one subject we can see very clearly like the states and how all these have some meaning, and in contrast to another subject, so that unlike classic analysis where we always, you see the whole group and you find some average, then you can see something. Here it's like, you can see all these very interesting individual differences in a very meaningful way.
Yeah.
So I think this class of analysis is very promising for that reason. Yeah.
Mm-hmm.
So very cool.
Yep. I think that's all.
Okay. Thank you. So for these scripts that you've given, we can just download, and I got it, and you can run it as it is. But if we want to do it for our own, do we have to change any path, or is it that we how do we, if let's say we have our project, how do we just use the script? Or do we need to change anything
I
first?
think you need to have the here package, the R package.
Okay.
So once you download this and you click this,
Which
and
one?
then I think you need
State
to set up.
MDS project, okay.
Yeah, I think you need to set up the path for your directory you want to use from this.
Where?
I think it's here, like in the upper right corner.
Oh, like state MDS,
Yeah.
and then I need to
Select your
project options,
path.
is it?
Yeah.
Where? Project option. Oh, open. No. Project options. How do I set the path?
New project.
Will that make this
I
state?
think, from my understanding, if you download the here package in
Yeah.
R,
Yeah.
once you open these R projects, it will just
Oh, it will automatically
yeah.
know the relative
yeah.
paths and all that. Okay.
So you can't just open the R scripts first. You
Okay.
can't do it. You need
Yep.
to open the R project first.
Project first. Okay.
Yep.
Got it. So then as long as if I put my data in the same, if I go back to the Finder
Yeah.
and I put it into same like the data, and my scripts are in R, and my data have the raw and the voxels, it will be able to you know to look at raw voxels and then all this CSV file and then do those things.
But for
Yeah.
the row, from the 4D API volume, it requires MATLAB.
Right. So that's not what is done here.
Yeah.
You've already done the cat carrying voxel on this thing for subject 1, but actually there are 6 subjects,
Yeah.
right? And so for this subject, you have used the mask from the DMN, and then you have used cat carrying voxel to apply onto this volume,
Yeah.
and then it has created the CSV
Yeah.
file.
Here. the
Okay,
voxel.
so this assumes that all our nifty data 4D volume have been pre-processed and cleaned up, and it's in subject space, or it can be in normalized space, but that's assuming the mask and the volume are in the same space. Then you use cat carrying voxel to extract that and give you this CSV.
Yep.
And this one, the CSV are, you said that it's DMN only.
No,
So-
actually,
Huh?
it doesn't match.
Oh, what do you mean?
The row I provide here is from the younger
Oh,
adults.
not this subject one, you
Oh,
mean?
no.
It's another subject,
yeah,
but
yeah.
it doesn't matter. So in theory, when we apply the cat carrying voxel in MATLAB to this, we will get the CSV for subject 1's
Yeah.
DMN mask or whatever that
Yeah.
mask is. And that will be, the mask is, every row is a time point, every column is a voxel.
Yeah.
But then, so this is, the mask is 1 ROI. But if my mask is the whole brain, then I will have like a lot of voxels. In this case, how many voxels were there? I forgot.
It varies.
But roughly about in the order of hundreds or thousands?
Maybe hundreds.
Hundreds. So the speed was pretty fast. It did it like for
Yeah.
6 subjects or 8 subjects, it did it all within a few seconds.
Actually, the voxels, the CSV file I provide here, is from the Defumo
Oh,
atlas,
okay.
so it will be like even smaller. So the
Okay.
voxel size is just like 100, 300. But for our
Oh,
AL,
because the Defumo ROI parcels are smaller.
Yeah, yeah.
So, okay. Got
but
it.
for when we use the AL3 atlas to get the DMN network,
That one is
it
bigger.
will be like 3,000, 4,000.
And was it
voxels.
very significantly longer or roughly the same?
Slightly longer, but still.
Longer doesn't mean like a whole day,
No.
just like
Yeah.
a few more minutes
Yeah.
or seconds. Okay. All right. Okay, so I think that's it. Anyone have questions?
I think Chennai making the figures using the R looks really pretty, and
Oh, I asked Gemini.
anyway, and then the speed it processing the figures and images looks quite faster than we use like Python or those things.
Oh,
Is it?
really?
I'm asking you.
Maybe
because-
I just changed my new MacBook Air.
Uh-huh.
Oh, no, I ran it on, this one is 2021 or 2.
Ah,
It's an M1 chip.
mm,
It's pretty fast.
mm.
Yeah. Yours is also, right?
Mine M2.
So, but it's quite fast, right? So I think it's fast because, is it because the MDS script has been optimized? I think the key is the MDS part. The heart of it is the MDS, where you take every voxel and then you project it. You have to calculate like, okay, so how do I want to project it and find the right dimension to project it. But the MDS algorithm is actually a very simple, it's not a very complicated
It's
one.
already preset on the.
It's in R.
In the
Where was it in the
package,
script?
It's a,
Where is the
from,
key line in the script that does the MDS?
Here, Maytown MDS.
That's the R function.
Mhm.
So that is the key function. Yeah. So yeah, I use Euclidean distance, but you can also use other distances, right? But here we use Euclidean, and because we don't have any other assumption, it's like you just occupy some 3D space or 4D space or whatever, how many D space. The thing is that this is the heart, and this is very optimized already because MDS is such a basic statistical thing. Yeah. We said we want to try, what's that one, the other one? UMAP, yeah.
I haven't checked it yet.
You can, so in other words, when it's UMAP, right, it will be replacing this MDS thing, but the rest will be the same, giving you some points, but based on UMAP's clustering or spreading algorithm, or projecting algorithm. Yeah. But that would be interesting to see if UMAP picks up something MDS does not. Yeah. Yeah, the other scripts takes a long time.
No, because we need to develop a way to set a figure for the GMFC Y method together. So I was thinking maybe I need to look into R function.
You can try R, but I would say part of the reason why this is faster is because the points are fewer. It is, like we say, how many thousand? 180 points.
Oh.
Yeah, so that's why
Just
it's so few. Compared to if we do the R, the the connectome is every voxel to every voxel is 10,000. So that's why a part of it is also, yeah. But I think Yancheng had a way from last week. He showed us that you can get the plot pretty fast as well. So I don't know how he optimized it, but from last week's or last week's scripts, we can see where are some optimization for speed. Yeah, and I think he used Python. He should be Python.
Yeah, he must be using Python, I think.
Okay, no problem. You can use R, MATLAB, Python, whichever works faster. For the visualization. Yeah.
So here, I want to show you like my current analysis. And this brain map, I use Python to plot. It takes maybe 1 or 2 minutes. Yeah. So here the first row is for the older adults, and second row is younger adults, and the third one is t-test. So you can see, this is for mean velocity, which you can get this number from the first R scripts I provided in the GitHub. So you can see the older subjects, they have lower mean velocity compared to the younger one. And this one is for the CHA, the space they travel. So again, the older adult, they travel less than the younger adults. For the entropy, it's the t-test is like almost like completely opposite. So here, older adults have higher entropy compared to younger adults. And also for the liminarity, it's still the same. Like the older adults has higher liminarity than the younger adult. Yeah, it's stuck somewhere. Okay. So this one, I use Diffumo at least, and I use 256 masks, the postulations. So actually, I run the MDS for 256 times per participant. Yeah, to get the value for
Whole
each
brain.
mask.
Yeah.
And then I average them and then plot on this brain map.
So, and all these are based on 180
Six.
TRs?
Yeah.
TR is 180 time points.
Yeah.
So which is about, what's it, 6 minutes? No, times two. 180
6 minutes.
TRs is 6 minutes, right?
Joe.
2 seconds, right? So,
Yeah.
so 360,
Yeah,
which is
yeah.
6 minutes.
Yeah.
So in 6 minutes, the older brain kind of change the state like in a very narrow way, but they move everywhere, but they move very slowly.
Yeah.
Because it's kind of like they get stuck, but they get very slow, but they move. They don't stay in one exact place, but they do kind of move around, but they move only in a few. So that's the quality of their state change. But the younger brain in 6 minutes does something like come here, go there, come here, go there, like that. Yeah, that's very interesting. Okay. Very cool.
Okay.
Okay, that's it. Any other questions? Anything else? Thank you, Junwei. All right.
Thank you.
So again, this is just an informal sharing, matter of record for our lab actually, more like so we remember when we have these tools that we develop and then how we use it, by the owners of the project, that they can guide us to use it. So we'll record this. I think they will give us the video in a few days' time. Then after that, we will put it as a log in the lab, but I'll also share it for the BrainHack school if people are interested. And then actually, we can even put this out as a YouTube clip. You can link it in the GitHub. So the GitHub, right, you can, if you do a tutorial, you can have and here's the YouTube clip for how to use it and all that. Yeah, so that'd be very cool.
Okay.
Okay, thank you.
Thank you.
All right, and thanks everyone. We're gonna log off from Google Meet now.
Bye bye.哦，应该可以啊，应该是蛮简单的啦。